Hello and welcome to Dunjun. I'm Bill, and this is the series where I'll be demonstrating and documenting the process of making a game from scratch. Today is day 17, and in today and tomorrow I'll be explaining complex numbers and quaternions, and I'll try to explain the concept of quaternions in an easy, understandable way, and why we use quaternions and how to visualize them and other reasons why we'd use quaternions instead of Euler angles and or matrices, and when not to use them and other circumstances. So these will take a while to do. Again, I'm splitting these up into the complex numbers part and the quaternions part, and I'm assuming you do know a bit of algebra and stuff like that, and some of these concepts may be foreign to you, so you're not used to them. But I'll start with the introduction. So in computer graphics, we have transformations again, and we've been using matrices to do that. However, when we express a transformation with a matrix, we can usually do the translation, the rotation, so the orientation in space, or its scale, or shear, as sometimes it's called, a different way of doing it. And you can think of that transformation as the basis for the space. So when you multiply a point or a vector or whatever, it transforms that vector into the basis space. Again, if you don't understand what I'm talking about, that's fine. Just that. And complex numbers and quaternions can be used to represent rotations or orientations in space. Complex numbers are to represent 2D or rotations, and quaternions are used to represent three-dimensional rotations. So that's the kind of quick preview of what complex numbers are and such. So before we can even start quaternions, we need to start complex numbers, and you may be understanding, what the hell are complex numbers? Well, in addition to all of the other types of numbers that we have, so we have, what type of numbers we have? We have natural numbers, and these are usually denoted by like a Z plus. Let's try that, the blackface one, yeah, Z plus, like that. So these natural numbers are 0, 1, 2, 3, 4. So yeah, all the positive whole numbers. We also have the integers. These are a Z just on its own. So these could be -1, -2, -37, 0, 3, 5. You can guess, they're all those there. They're examples. We also have the rational, and this is usually denoted with a Q, like a blackface Q. So rational numbers could be like 3 over 2, 7 over 3, 1 over 2, 1, -1, etc. Say 10 as well, whatever, I'm going to do another number. So these are the fractions, stuff we can express as a fraction. That's what irrational numbers are. Then we have the irrational numbers. Now, irrational, the symbol for them isn't, they haven't got a distinct symbol. They have, they kind of say it's the real numbers, which is denoted by this R, minus all the rational numbers. So they're what's left in the real numbers. That's the way to denote it. So irrational, like the square root of 2, the square root of 3. What else is there? There could be the golden ratio. That's irrational. And such numbers like that, you know, like the cube root of 3 or something like that. So usually these are the ones that are algebraically expressed. Irrational can only be expressed in algebraic numbers. And then the other set, again, as he's talking about, is real numbers. And the real numbers could be 1, 0, pi, tau, e. Trying to think some more of the numbers, just anything like that. So these are called the real numbers. So these are not expressible by algebraic expressions. So they're the kind of sets of numbers there are. Now I'm going to, in this number system, we're going to introduce some complex numbers. And the complex numbers, I'm not going to give any examples yet, are denoted with a boldface C. They're what the complex numbers are, and I'm going to put ... So I'm going to explain this. But first, before even complex numbers, we've got imaginary numbers. So I'm going to scroll down and talk about imaginary numbers. So imaginary numbers. So think of this equation here. I'm going to change the colour to a nice orange. So x squared plus 1. What are the solutions to that? Now, if you're normally thinking about this, this graph would look like, let's do it in green. It would look like, draw a bit better. So there's our function. We'll say that's the function of x, and that's x. The graph would look like this. So we don't actually, it never hits the line which is x equals y equals f of x equals 0. So this here. So it never goes through. So there are no solutions. Well, there's no real solutions. So to solve this equation here, so x squared equals -1, we know this is not possible in the real ways. So what we say is we create up a new number, an imaginary number as we call it. And we say, I'm going to put this in a big, let's say green this time again, let's go yellow. And we create a new imaginary number which has that solution. So we call it I. I squared is equal to -1. So I is the square root of -1, which is again the same implies that I equals the square root of -1, which doesn't make any sense. But again, this is imaginary. This is why mathematicians call it like that. And again, don't try and understand it that much, but it just seems to work and it pops up all over the place. And again, the complex numbers with these imaginary stuff, that's why they're called complex, we denote with this weird C symbol. So the normal way we normally write a complex number is, let's say z is our complex number, which equals a plus bi. Yeah? So we have z is the complex number, a plus bi, where a and b are both real numbers. So they could be any like that. And of course, I is the square root of -1. Yeah? And again, if we set, if b equals 0, then z is actually a real number. Yeah? However, if a equals 0, z now would equal a imaginary number, which is actually a boldface I for imaginary. But if a doesn't equal 0 and b doesn't equal 0, then z is a complex number. Hope that makes sense. Okay, good. So now we're going to do operations in complex numbers. So which colour was it? Is it that one? Yeah. Operations with complex numbers. Again, this will all be saved on the GitHub page, which is github.com/gingerbill/dungeon, and it'll be stored in data, then the Blackboard, and it's under blackboard.art, as you can see here. That's where the address is, same as the GitHub bit. So that's the operations with complex numbers. Now, again, the operations we can have are addition and subtraction, and it would work as you may think it would. So if we had, let's say A1 plus, I was doing a different colour, white. Let's do white, yeah. It's A1 plus B1I. Let's added that to A2 plus B2I. You just add the real components together and the imaginary components together, so you get A1 plus A2 plus B1 plus B2I. So that's how it works, yeah? And subtraction works exactly the same. So just do this a long way around. Subtract that. That's meant to be a plus. So the subtraction works exactly as you may think. Like that. So that is subtraction with complex numbers. Now we're going to do the product. So if we had two numbers, say Z1, which is again A1 plus B1I, and Z2, we said Z2 plus B2I. Just going to save that one. Let's go with long. If we did the product or the multiplication between two of them, so we do Z1 times Z2, what we have is A1 plus B1I multiplied by a2 plus b2i. If we just do expand them out, so we get a1 a2 times by a1 b2i. Next we do this one, so we've got b1i a2. I'm just writing it out as normally, and then this one would be b1 b2 I squared. Okay, well, let's tidy this up. So we've got the reals and the imaginaries together. So this is going to be a real, and this is going to be real. So I remember I squared was -1, so this actually now equals b1 minus b2, and then there's the imaginary parts. So you got a1 b2 plus b1 a2 I. So that is the product. And again, if you did squaring, you could do like the square of a complex number. So if you had z squared, this would be the same as a plus bi squared, which would be a plus bi times a plus bi, which would be, if you expanded it out, you've got a times a, so a squared, then you've got bi times bi, which minus bi, it's 2a bi. Okay, oops, wow. Just hit my mouse rather than my pen. So that is the square of a complex number. And you may be noticing something along. If you mess around with this, you may have noticed you can do something else with this. And there's something called the complex conjugate. Yeah. So the complex conjugate. Now, I've seen both notations, and I still use both, depending on the series. But the complex conjugate is when the imaginary part of the number is made negative or negated or whatever. I can't think of the proper word. So if you had the number z, which equals a plus bi, the complex conjugate is either denoted with z star, or it's usually z bar. Either one is common. You'll see both in textbooks. I've seen both quite a lot, actually. So they flip and change it between. In some certain circumstances, one's better than the other, but again, they mean the same thing. And just be consistent. That's all I want to say. So that's what it means. So z, I'm just going to stay with z star. Z star is equal to a minus bi. So what you do is you're negating the imaginary part of z. So there's the two differences, yeah. So what you're maybe asking is, okay, what happens if I do z times z star? Well, if I just write this out longhand, it's minus bi. So let's do it longhand. So we do a times a, so we've got a squared. So we've got b times a I, and what we've got here is times it again, we've got negative a bi, and then we've got minus b squared I squared. These two cancel out, and the I squared becomes -1, so what we've got is a squared plus b squared, which may sound, oh, that looks a bit familiar. You've seen this Pythagoras coming out of here, like a Pythagoras, I squared plus b squared equals c squared. Okay. Well, this is actually useful, and this is what we call we can get the magnitude of a number. So if we had z, the magnitude is usually represented with two lines of z, again, is the magnitude of a plus bi, can be written, so z can be written as the square root of z star. Again, it's just Pythagorean theorem. Or another way of writing that would be the same as me writing a squared plus b squared, or z times z star equals a squared plus b squared. So which is again the magnitude squared. Some people call this the norm. I got taught this was the magnitude. It doesn't really matter. Again, both conventions are used. The magnitude makes a bit more sense than calling it the norm, in my opinion. So that are some of the basic functions you can do. What else is that? There's division. You can do division as well with complex numbers. So division, also known or it's called the quotient, I think. I think that's the technical term. The quotient. So if you had again Z1, which equals A1 plus B1I, and Z2, which is A2 plus B2I. If we were going to do Z1 over Z2, this would equal A1 plus B1I over A2 plus B2I. Now we can leave it like that, and that makes perfect sense. However, most of the time we don't want to be working with complex numbers as a fraction underneath. And usually we just want to turn it back into a normal number, like a normal complex number. And as a mathematician, the trick is usually called times in by 1. And that makes it sound like times it by unity. It's like, what? It's mathematical tricks to actually get stuff. So what we do here is we actually multiply by 1. And I don't mean a special type of 1. So it's A2 by B2. And if anyone you can think out there, what do we do to get rid of this and make this into a real number at the bottom, but still keep this to be imaginary at the top? Yes, we multiply it by its complex conjugate at the bottom. So what I'm going to do is multiply it by 1, A2 minus B2I times A2 minus B2I. It's a nice little trick. We multiply these all out. What we get under the base is we get what we get is A2 squared plus B2 squared, and then what we get on top, I'm just going to quickly go through it. What we get is A1 A2 plus B1 B2. So that's our real part. The imaginary part is B1 A2 minus A1 B2 minus A1 B2. Yeah, that's correct. So I've just done that. So that's what you get, and this is I. Yeah. So this is our real part, and that's imaginary part. So what we've done here is we're normalizing it by dividing by the square magnitude of Z2. And again, if we rewrite this out, now what we've got is the real part over the magnitude. That's our real part, plus the imaginary part. And there we go, we've got rid of this complex quotient or fraction or whatever. Okay, that's our complex numbers. So next thing we can go on to is, what else is there to talk about complex numbers? Oh, powers of I, that might be useful. I'm just looking on the Wikipedia article here. Powers of I. So what I mean by that is if you've got I to the n, let's just say n here, and then I to the n, let's just do a little table like that. Now let's just get a straight line to do it. It'd be much easier to draw like tables like this. Aha! There we go. And back to the brush. I make it white. So if we had 0, 1, 2, 3, 4, 5, just go up to 5 be enough for now, and you'll see the pattern. So what we've got is anything to the power of 0 is usually 1, except 0, but yeah, so anything to the power of 0 is 1. Now I to the 1, actually I'm going to write this out, so I'm going to just say I to the 0 equals 1. I to the 1 equals I, so it's unchanged. I to the 2, as we said, was negative 1. Then we've got I to the 3, which is negative 1 times I, which is negative I. Yeah, you can see where the pattern's coming from. I to the 4 is I squared times I squared, which is plus 1. I'll put plus there as well. And then I to the 5 equals I to the 4 times I, which is I. So you can see the pattern. And the way in computing we might write this, or any maths in particular, is I to the n so I to the n is equal to how would we write this? What's the better way of writing it? It would I to the n equals 1 I is the same as what me writing is this keeps. It's the same sequence as writing as 1 I negative 1 negative I dot 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 1 I negative 1 negative I dot dot dot. So it's that sequence. So the sequence repeats for n mod 4. That's another way of writing it. That's the repeat. Yeah. Okay, so this is a repeating sequence, and it's very nice to understand this. And yeah, let's just go back down now, and let's talk about expressing numbers on the complex plane. That's a nice way of doing it. So I'm going to get the drawing thing out. Let's to a green number. Why not just green for the hell of it? So normally we're used to seeing graphs like so, where we've got. Let's do that. We have an x and a y, something like that, yeah? So this is normally how we write numbers. So we have an x value and an y value like that. We say it's this point here, this is at value of a, b, yeah? Whatever, this point here or that point there is at c, d, I don't know, I'm just making this up. Okay, they're just points on a graph. Another way to do it, I think, of representing complex numbers is something called an Argand diagram. Now these are, again, what we do is replace the x and the y with the real component and the imaginary component. So I write imag and real. Imaginary. So the imaginary and the real component. So if you had a number, let's go here, this point here, and this was at a, b, that point there would actually, that means that implies the same as a plus bi, because we've gone a across the real axis, so which is where a is, and then we've gone up b up the imaginary axis. So that is what this is. So yeah, we can express it as a thing, like a. You can express it as in an Argand diagram. So let's think of an example. So let's go back down and actually draw an Argand diagram. So let's draw a better one this time with a line like so, like that. And let's choose a point, and I'm just going to roughly mark these. Red might not be the best colour actually, I'm just going to try an orange instead. So I'm just making some divisions on here. It's about circular, it's about square, isn't it? Yeah. Let's say we have a new point, and I'm going to choose the point 1 plus 2i. So here's this point here. Oops, get back to the brush. So let's choose, I'm going to do it in purple, I'm going to choose this point here. Just drawing the things on here as well. So that is the imaginary, and that's the real space. And these again, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, 1, 2, 3, negative 1, negative 2, negative 3, and they're all the I components. So we're going to choose point x across there, and the x point, we're just going to denote this as point p. So p for point. So p is also is equal to 1 plus 2i, which we can represent as 1, 2. Okay? So now we've put these onto a complex plane. The next number I'm going to do is I'm going to multiply this p by I. So I'm going to say q equals pi. So p times I, not pi or pi, magnum pi. What I'm going to do is multiply all these by I, and what we get is negative 2 plus I. Yeah, that's what q is. I'm going to denote q on this circle. So it's negative 2 I, so it's there. And that's where q is. The next number I'm going to say is, what's after q? Is it r? Yeah, r. I'm going to times that by I as well, and this is going to be negative 1 minus 2i. We're going to put that on a graph. So where's negative 2? Negative 1, negative 2, so here. And that's at r. I'm going to say r's there. And then we've got s. Let's do it again, multiply by I. And you might be wondering why I'm doing all this I, and you may notice it in a minute. So what we got is 2 minus I. So we're going to go to 2 minus I. and that's where S is. Again, I'm not using proper graph paper or anything like that, so it probably doesn't work. But as you may have noticed, those are opposite, and they go through the origin. They're meant to, anyway. And those are opposite, and go through the origin as well. It's not brilliant drawing. And all these numbers actually lie on a circle. Oops. Wow, okay, so all of these numbers that you've done, gone to P to Q to R to S, I've multiplied these by I every time, and they've been rotated, oops, I'll go back to the brush, they've been rotated here counterclockwise by 90 degrees. So every time we times by I, we rotate by 90 degrees in the complex plane. And that's pretty useful. And again, we've kept the length to be the same. So the length of this complex number, I'm doing the norm, the square root of the norm, or the square root of the magnitude of it, is always constant. So it's kept to this unit circle, where this unit circle's radius, the radius of that circle, so the radius of circle is actually equal to P star square rooted, which turns out to be 1 plus 2 squared, 1 squared plus 2 squared squared, which equals root 5. So the length of this is kept the same. And this is why we can express them as rotations. So I times by I rotates by 90 degrees every time. So if we multiplied by I squared, so -1, we rotate by I, what's it called, 880 degrees, and I cubed, we go to the 270, and I to the 4th, we go back to nothing, we get back to its starting position. So the times we multiply by I rotates by 90 degrees counterclockwise, and that's why we've been using counterclockwise rotations in our calculations for the code anyway. So this brings us up to rotations. So let's do in orange again, so rotations and rotors, like so. Again, if we had Z, let's go back to Z. So Z is, we can express this as A plus BI, yeah? If we say that we had a number Z plus BI, and then we had a rotation, well, we're going to denote this by Q, and again, this is just to keep with the rotations of quaternions later on. And we had Q as our rotation, and we can express a rotation in complex numbers as cosine theta, so theta's being the angle we rotate by, plus I sine theta. And this may sound a bit bizarre, like, where the hell did that pop out from, and how did we know this? Well, I'm going to show you just to see that it works, and we're going to... So when we rotate this, what we do is, we can rotate many things out like this. So what we do is, I'm just trying to think of how to do this, best way to do it. Yeah, so if we had Z times by Q, so that's the same as me writing BI times by all that, cosine theta, plus I sine theta. When we expand this out, what we get is A cosine theta minus B sine theta, that's our real part, plus of A sine theta plus B cosine theta I. So that is our imaginary part. So that's what happens when we expand those brackets out. And you're thinking, okay, that doesn't make any sense. So let's try and do the same thing here. So let's rotate by 90 degrees, yeah? So, and let's say, so if we rotate counterclockwise, do it again, purple. If we rotate by counterclockwise by 90 degrees, this means that theta, again, theta now equals 90 degrees because that's the convention we're using. So input here, so Z times Q, and now I'm going to put 90 degrees in here everywhere. So A cosine 90 degrees. If you want to use pi over 2 or tau over 4, it doesn't matter, you can use it in radians, so that's pi over 2 or tau over 4, whichever notation you're using. If you want to use radians or degrees, I'm just using degrees because most people are more familiar with them. So let's do sine of 90 degrees plus a sine theta, a of sine 90 degrees plus b of cosine of 90 degrees. So the cosine of 90 is 0, so that becomes 0, and the cosine of sine of 90 is 1, so that becomes negative b. Do it here, the sine of 90 is that, so we've got bai, and cosine of 90 is 0. So what we've done here is rotated by 90 degrees, this complex number, and what we've done is got, this is the same as me writing z times I. So that's what we've done. We've rotated by 90 degrees, and that's a way of actually using complex numbers to rotate things. And you may be still a bit confused, like saying, but we've just rotated a complex number around. How is that any useful? Well, how to get onto that now? So representing complex numbers as matrices. So let's go back to that z equals a plus bi. Z can be mapped, that's the symbol for mapped on, as a matrix of a minus b, ba. So that is how you map a complex number into a matrix. Yeah? So if you want to multiply two complex numbers, you just do multiply two of these. Simple enough. And to get the complex conjugate of z, that's actually the same as me doing z transposed. So that become a minus b, ba transposed. That means we now flip it across the diagonal axis, which becomes b minus ba. So it's another way of representing a complex number as a matrix. Now, this matrix is a 2 by 2 matrix, as you may have noticed again. And this means what we're doing is rotations in 2 by 2 dimensional space. So if we had put the cosine sine theta back in, so we had q, this gets mapped onto cosine theta minus sine theta, sine theta, cosine theta, like so. Now, if we wanted to rotate a point in like at the xy plane, all we have to do is q multiplied by a point p, where p actually equals x and y. We can do q times by p, and this is actually the same as me writing the matrix of cosine minus sine theta, like so, times by x, y. So what we're doing is that the imaginary part of the complex number represents y, because it's technically 90 degrees to x. It's been y has been 90 degrees rotated of x, and x is the real component, so the x component, so this is it. And if we expanded this out, we get the same formula as we did there. So that's actually rotating in 2 dimensions with complex numbers. And again, I may have not explained why I said the rotation complex number was cosine theta plus sine theta. Now, the reason why is if we get the times that by its complex conjugate, what we get is cosine squared theta plus sine squared theta. And this is an identity which we know as 1. And it's just one of those identities where cosine squared theta plus sine squared theta equals 1. And that means what we're doing with this rotation is we're not actually scaling the position anymore, so we're keeping it the same length. And that means that this thing won't get scaled, it won't get sheared as it's called. We're just rotating it, which is a very good thing to do usually. And you still may be wondering, where does this come from? Well, that's the last thing I'm going to talk about, which is Eulers Formula. And many of you out there, you may have seen this, if you've seen complex numbers before, you may have seen e to the pi I pi equals -1 or something around that, or e to the pi I plus 1 equals 0, or something like that. And this is a very famous formula, or you may have seen I to the tau equals 1. You may have seen, I don't know what, any of these formulas before, you may have done. And you may be wondering, okay, so we've got an e, an I and a pi, and then plus 1 to it, and you get 0. What? Huh? So how does this come about? Well, this pi, again, and this I, as we learned, i's and pi's we can use for rotation. So e to the I theta can represent a complex number. And this can be represented as cosine theta plus I sine theta. The proof for it is a little weird. You can still look out there, but it talks about doing series. So e to the x, like that, can be expressed as 1 plus x plus x squared over 2, x squared over 2, is it over 2, yeah? Plus x cubed over 3, and yada yada yada. So some resources for this. This is Eulers Formula, yeah? So the proof, where's the proof on this? I think I just need to check. Come on, is it on here somewhere or not? Oh, here we go, here's the proof. So this is, yeah, it's 2 factorial. I knew there's a factorial in there somewhere. So it's, brush, white, 2 factorial plus x cubed over 3 factorial, etc. Yeah? So that's how we express a complex number, the exponential thing. Now if we put e to the I, the x in there, just keep it instead of the theta, what we get is 1 plus ix plus ix squared over 2 factorial plus ix cubed over 3 factorial plus dot dot dot. Yeah? That's one way of expressing it. Now if we expand this out, what we get is 1 plus ix, okay, plus negative x squared over 2 factorial minus ix cubed over 3 factorial plus dot dot dot, yeah? And if we separate these into the real parts and the imaginary parts, what we get is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial plus dot dot dot, plus the imaginary part, which is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial dot dot dot, whatever, oops, minus dot dot dot. So that's what the series expands out to. And this is actually the expansion, this is the Taylor's expansion or Maclaurin expansion of cosine x. And that is actually the expansion of sine x. And what we've done is this, we've proven Eulers formula where e to the I theta equals cosine theta plus I sine theta. Like so. And again, going back to that graph up here, we've got a massive circle, and we said this radius was root 5. But as we explained here, this cosine theta, I sine theta, is got a length of 1. So to represent any number as an exponential, z could be expressed as r, where r is the length of e to the I theta. And r, where r is actually r squared equals a squared plus b squared, if this is also equal to za plus ib. And theta, another way of writing theta, would be the arc tan of b over a. And that can be easily proven with just triangles. So if we get another triangle here, like so, this is A, oops, that's A, that's B, that's theta, and to calculate it you do SOHCAHTOA, so B over A equals tan theta. So that's it. So Z can now be written as Z, oops, that's 2, Z equals the square root of a squared plus b squared times e to the I arc tan b over a. And again, this theta represents an angle. So if we kept adding on, let's say 90 degrees or pi or whatever it is, we'd rotate around this circle of radius r. So that's what we kept doing, yeah? Let's go back down, 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 down. So that is how we express our complex numbers in terms of the exponential number, I, and its radius. Instead of doing a plus ib, we have now got its magnitude and its rotation. So that is kind of a brief introduction to complex numbers. Again, I'm not expecting you to understand this straight away. Please do read up, and it's very interesting about complex numbers. So stay tuned for tomorrow, where I'll be going on to talk about quaternions and how quaternions are the analogous of complex numbers, but in three-dimensional space. So stay tuned for that, and goodbye.